Hey, welcome to my channel. Today I'm going to be talking about compute and storage. As an introduction, I would say that when you're a data analyst, most of the words that you hear has to do with dashboards and graphs, charts, and all of that. When you become a data engineer, there are two words you will hear all your life, and it's compute and storage. These are the core building blocks of any data platform, whether it's a traditional database, a Hadoop cluster, or a modern cloud warehouse like BigQuery, Snowflake, Databricks. These are two words you hear because all of modern data infrastructure is built around these two things, the compute and the storage. And really, when you talk about storage, one key thing that comes to mind is data. So think about storage in terms of data. Storage is simply where your data lives. A good analogy I can give to understand what storage is about is think about bookshelves. Of course, you know what bookshelves is. When you go to the library, you have the bookshelves. The bookshelf hold the books, the journals, and papers, just like storage holds rows, tables, and files. So within your storage, you have it holding your rows, your tables, holding files, and you name them. The same thing happens within bookshelves because the bookshelf tries to hold your journals, your papers, and just like that. So think about storage in this context. Your storage is anything that helps you to hold this. In a database world, storage might be disk attached to a server. It could be in the cloud where you have storage is usually object storage like Google Cloud Storage, Amazon Storage, or Azure Data Lake Storage. The key characteristics about the storage is number one, storage is persistent. By persistent, it means that the data stays there until you delete the data. And two is that because we now live in the modern data landscape where most of the data live in cloud, storage is cheap. Storing a terabyte is far less costly than processing a terabyte. When you want to process the data is more expensive than when you want to store the data. And number three is that storage is scalable. You could scale the storage. The modern storage can hold petabyte of data or more. You can actually scale it as much as you want to. So if we can come back to our analogy of the bookcase, the bookshelf does not read or summarize the book for you. It just holds it safely until you need it. So all of the journals that it has, all of the papers, it doesn't do anything about them. It just holds them. And because it just holds them, it's the same thing that happens within your storage. Your storage is persistent, is cheap, is scalable, and all of these rows and files of data that is held within your storage, nothing happens to this. If storage is all you have within your data infrastructure, you cannot do anything with your data. And that is where the compute comes in. And what is compute? Compute is the power that processes the data. And compute helps you to make sense of all of this data that you've already stored within your system. Without the compute, you cannot do anything about it. If we can go back to the analogy of the library, if storage is the bookshelf, compute is what you could call the librarian. The compute is the librarian who fetches the books, reads them, and answers your question. If you want to know anything about the whole data you have, all of the journals, the papers, and everything you have within your system, the person that helps you make sense of it is the librarian. And that is where the compute comes into play. In a more technical term, your compute refers to one, CPU. The CPU is the central processing unit. It helps you to execute instructions within your system. You also have the memory. It holds data temporarily while calculations happen. And finally, within your compute, you also have the GPU. The GPU is accelerators for machine learning or complex mathematics that you have within your system. So whenever you run a SQL query, you train a machine learning model, or you do aggregation of logs, it's compute doing the heavy lifting. All of the processes that you do executions, all of those things is being done by the compute. And so compute and storage, these are the key components of what makes the data landscape possible. And to give you a bit of characteristics of the compute is one is ephemeral. It means that you spin it up when you need it and you shut it down when you don't need it. Compute, you call it when you want it to work and you stop it when you don't want it to work. The second part is expensive. Compute is quite expensive. When you're processing terabytes, can cost far more than storing them. And finally, compute is flexible. You can scale it up, more CPUs, more memory to go faster or down to save cost. And it can scale up just like you have scalable for the data. You can also scale up the compute as much as you want. It's flexible in that sense. And going back to our analogy again, the librarian works while you ask a question. Once they are done, you don't pay them to sit around. So if you need something from the librarian, you go to the librarian and you say, I want to clarify this question. And when they are done, they go back to what they're doing. And it's the same thing with compute. You call the clusters, you call the servers when you want them to work. You call all of these nodes and they help you process what you want to do. And they go back to sleep, or they go back to work for somebody else, or answer another customer or another person that wants to use the services of the librarian. And that is how it works. You call up this compute, you do what you want to do, and the compute go back when you are done with it. They just don't sit around. Okay, let's talk about a traditional approach. For decades, compute and storage were tightly bound together. So for a long time, you have the compute and storage as a single unit. They were tightly bound together in a single system. Example of this is your Oracle, your SQL Server, Hadoop in the early days. And even the early days of Redshift, you had this bundling together of the compute and storage. Data lived on disk inside the server, and that same server has the CPU and memory and processed all of the query that you want to run. And most of the people that started their data engineering career maybe like 10 years ago, 7 years ago, 15 years ago, and back then, you understand what it means to have the compute and the storage bundled together as a single unit. What is meant is that if you needed more storage, you had to buy more servers, which also added compute. You cannot increase one without increasing the other. So both of them must be scaled together. If you needed more compute, you also needed to get more storage. So you buy more servers, which also added storage. Scaling was rigid, costly, and very, very inefficient. So think about it in the analogy that we were using, the bookshelves and the library analogy. What it meant is that every time you wanted more librarians, you also had to build more shelves, even if you didn't need them. Let's say you started having more people coming to the libraries and you needed to add more librarians to be able to cater for the people that are coming for their queries to ask questions and have them answered. What it meant is that for every librarian you add, you needed to also scale up the bookshelves. Even though people are not borrowing more books or they're not reading more books, for every time you needed to scale the librarians, you needed to add more bookshelves. And anytime you needed to scale the bookshelves, you also needed to scale the librarians. You can't scale one without the other. And this was a problem because it was very costly for businesses to be able to do that. When you come to the modern data approach, so this leads us to the modern approach. And in the modern approach, you have the separation of compute and storage. So these two are now separated. Storage became cheap. Scalable cloud storage stores like S3, GCP, and ADLS, they became very, very cheap if you want to just store your data. And compute became independent. You have clusters of servers, resources that you can spin up on demand. Some of the benefits of this, as you may ask, is one. So some of the benefits of this is number one, you had independent scaling. If you need it faster, you need your queries to be faster, you just had to add more compute only. And also, if your data is growing fast, you can easily expand storage only and not expand the compute. Number two is cost efficiency. You don't pay for compute when you are not using it. For storage, the storage costs are predictable and low. You actually know what you're going to use and it becomes very predictable for you. So number three is that you have multi-workload flexibility. You have different teams being able to run their own compute clusters on the same data. Everybody has the same data storage and you are able to run your own compute independently on the same data and everything is separated. And that multi-load flexibility is quite a great win because you can now have more teams working on data and they are distributed across your domains. So an example is you have the BI team running the dashboards. You have the ML team training models without stepping on each other's toes. You can even have the data engineering running their pipelines. And all of this can work concurrently because the compute are different and they can individually run their own clusters independently. And of course, the fourth is reliability. The data stays safe in storage even if compute crashes. You know your data is safe. In the traditional model, if anything happened to the compute, it happened to the storage. If anything happened to the storage, it happened to the compute because they were all bonded up together and they were a single unit. But because they are now separated, it becomes more reliable and you can know that if something happens to one, it's not going to affect the other one. So compute can come and go without risking the underlying data. So why does this matter to you as a data engineer? As a beginner or you've already started your career, this is why you should care about this. Why you should care is number one, architecture choices. Knowing whether a platform separates compute and storage tells you how scalable and cost effective it's going to be. And you have that idea when you are trying to work on a project, build a data product, and you are asked to design what the architecture should look like or recommend on the choices in terms of the tech stack to be used for the architecture design. If you have this understanding on how compute and storage works, it really helps you in designing of this kind of systems. And number two is performance tuning. And with performance tuning, really, instead of guessing if you need more disk or CPUs, you can target just what you need and you have that context, that kind of background to be able to decide on what goes or what doesn't come. And this is also important when it's time to schedule your jobs. You can schedule compute clusters to spin up only when needed. That's when you are designing your ETL jobs, your ML training models, and your dashboards. You can save cost incredibly if you understand how this works, and it's going to inform how you set up your job and you know what cluster to set up and what kind of configuration to use within your compute clusters. Yeah, the next one is really about your career. That's the biggest one. Because some of the biggest platforms we have today, talking about BigQuery, Snowflake, Databricks, they all rely on this separation because they are the modern data stack that almost every business is building their data around. And if you understand this foundational knowledge, you have the concept to be able to get on the interview, explain this foundational concept, and you prove to your hiring manager that you understand the foundations, and it really helps you within your career scaling. So it's a good career prospect for you to have. And that is it really on the compute and storage. I hope this video was helpful. Please like and subscribe if you have not, and to help us to do more of this video and to encourage others to be able to see the video. I do more content like this, so please check it out, other content that I've done. And I intend to do more video where I do this kind of breakdown to explain some of these tough concepts to understand. And I'm going to see you in the next one. Thank you for watching. Bye for now.